Hello, welcome to RF Design Tutorials, a playlist on my YouTube channel where we talk about practical RF and microwave circuit design. This is tutorial 10 on the topic low noise amplifier design, and this is a continuation of the tutorial 9. So if you haven't watched tutorial 9 until now, I would recommend you to please go ahead and watch tutorial 9 first before you continue on with this particular tutorial. Now in this tutorial, we are going to start from part 2. We already covered this agenda in the tutorial 9 of the video, and these are all sequential topic, and that's why I recommend you to watch tutorial 9 if you haven't done so already. So in this tutorial, we will go over the part 2 and part 3 of the design flow, and finally do the benchmark of our design with a off-the-shelf component available. Right, so enjoy the learning experience, and I hope after spending 1 hour on this tutorial video you will be fully equipped to start designing your own LNA circuits with the great confidence. Now before we start, subscribe to my channel. Once you already subscribed, don't forget to hit the bell icon to make sure all the notifications I enable. Also, your likes on my video is very important. Feel free to give it a thumbs up if you like the content presented, and click on the share button to share it with your friends, colleagues, and post the link on the LinkedIn or other forums you may be member of. That would be a great help from your side to me, and I thank you in advance for doing so. So let's get started and continue our learning and come up with a nice LNA circuit design. Hi, welcome to part 2 of this tutorial session. I hope you had a good break. So in part 2, we are going to talk about how to do impedance matching network design for circuit like LNA. And then we will look at a few tips and tricks on managing layout and EM simulation, and finally finish it off by EM circuit co-simulation. Now, before we start, just a quick revision, just in case you took a long break. So in the first part, we talked about stability network design, and we went through various consideration where designer need to take in order to achieve a decent stability without sacrificing too much of gain and noise figure while doing so. After that, we also talked about how a typical bias network design could be approached, and we shared we talked about few tips and tricks again in managing a proper bias network, and we ensured our bias network has an excellent performance at the frequency range we are looking at. So now we go ahead and talk about matching network in part 2. And first of the things which we want to do for matching network discussion here, you can notice this is my test circuit. And first thing which might catch your eye, that the RC network which we originally had, I also employed the same footprint modeling technique here. And also for the output stability network, I have done the same. This ensures that all the discontinuities, all the effects of these additional footprints which might affect our FET operating point is all duly captured with. And I don't want to leave all these things till the very end, which might force me to rework the whole stuff. At the input and output, you can notice I have a bias network design. And if I push inside is the same bias network, which we talked about during the last part. And here to make it suitable for subnetwork, I have disabled the 50 ohm terminations, which we had for our S parameter analysis, as well as I have disabled the S parameter controller from here. So the same bias network is utilized at both input and output side. All right, so with the right components in place, we can go ahead and run S parameter simulation. And while performing the impedance matching requirement, we may need to look at variety of measurements. And those measurements, if you recall in one of the earlier videos on S parameter simulation, we talked about max gain, power gain, gain circle, noise circles, and all that. So you could place any of these measurements on a schematic. However, the problem or the thing which I have tried avoiding is placing too many measurement functions on the schematic, because that kind of clutters the schematic representation. Instead, I have created a new schematic, and in this schematic I have placed all those measurements which I want to do, including the options block. that schematic, I also created a symbol so that I can represent it correctly into my main design. And the same thing you can see, I can just drag and drop this schematic onto my LNA design page, and these measurements are here. So if I push inside to this measurement, you can notice all the measurement which I'm going to use. So I do have gamma optimum and Z optimum, max gain, power gain, gain circle, noise circle, and all these measurements defined under this schematic page. So this is again often a very useful trick to clean up the schematic and make it more readable for yourself. Now let's go ahead and perform simulation. Now I already have this data display page set up, and initially when you look at it, you might get overwhelmed. No need to. Let's go each section by each section. So here in the first section, I have the same 4 plots which we also looked earlier. So I have the stability. I have the S21 plotted here, the noise figure and noise figure minimum, as well as S11 and S22 plotted here. Along with these 4 plots, I also have a gain and noise circle plotted here. And again, here you can see I have 3 circles each, which can also be seen under watt function. So in one of the earlier tutorials, we talked about watt function. So when you type watt and gain circle is the measurement name of this plot here, we can see it's producing 3 gain circles, 41 frequency points. So total number of circles will be 41 into 3. And then each circle is represented by 52 points. However, here you can see I only have 3 circles because I just filtered everything based on this marker M10 location. And the simple syntax to be used here is I only filter the frequency. You can see second argument is my frequency. So I type that argument with M10 frequency index. And I do have a slider here. And again, I have a previous tutorial talking about how to insert slider. You can do so by going to insert slider. Now, when I change this marker, you can notice how the gain and the noise circle changes because it is showing you response of your circuit depending on the frequency which you are plotting. So at 2.4 gigahertz, I can notice 3 noise figure circle and 3 gain circle. But what is that they are representing? So if I go back into my measurement block and look at the definition, so in noise circle, I'm plotting 1.1 dB, 1.2 and 1.3 dB, 3 noise circles here. And also for the gain circle, I'm plotting 14 dB, 15 dB and 16 dB gain circles. Again, you can set it as per your expectation, what you're looking at. I have set it to 14 to 16 because I minimum needed 14 dB gain. And I just wanted to have additional 2 circles to see which is the area which might give me little additional cushion on top of 14 dB to account for any additional loss which I may have in the further design step. All right, so this is how it is set up. And let's go back to data display. This is this section. And now if we look at the S11 and S22 plot here, now S22 is pretty straightforward because you just need to plot S22, place your marker at your desired location, unnormalize the readout of this marker, and you can notice the impedance directly there. So there's no big deal here. The fun or the main consideration in LNA design is how are you going to handle the input matching response. So here, let's focus on that. So on this Smith chart, you can see I have 2 plots, S optimum, which is nothing but gamma optimum for the best noise matching. And I have regular S11 plot. And I have placed 2 markers, M5 and M6. So M5 marker at 2.4 gigahertz tells you the best possible conjugate match, impedance. And M6 marker, which is on gamma optimum, is telling you what impedance you should prefer in order to obtain the NF minimum or the optimum noise figure from this device. Now, refer to our earlier discussion during fundamentals, I told that these 2 points will hardly agree with each other, and you can see they are different. So now the question which designer needs to ask himself is whether to go for this matching or that matching. And some designers have, different designers have different way of approaching this. So one set of designer may want to place a virtual point here and say, okay, we do a 50% compromise between these two, and this is like a halfway between these two requirements. And the way I have plotted this target gamma, measurement can be seen here. So I just decided target gamma, and you can see this is 0.3 constant resistance circle. This is minus zero point 0.1 point, and I want to be here. So I just define that in a new equation and renormalize it to 50 ohm. And then I calculate target gamma using the simple formula, which we have all read in our undergraduate days. So that's your target, impedance, which might give you the midway point. That's approach number one. The second set of designer might rely more on looking at, gain and noise circle. So here you can notice I have this M8 marker, which is basically placed on the gain circles. And currently the outermost circle is the 14 dB. And that's why you can see it's the biggest circle, because more impedances can produce that kind of gain. And as soon as you start increasing the gain, let's say the innermost circle gives you around 16 dB of gain from that device. And these are constant gain circles. So no matter which point you are onto this circle, if you match your amplifier to that particular impedance, you will get the gain which you are looking for. Similarly, there are three noise circles here, and the outermost noise circle is the poorest of them, right? So it's 1.3 dB noise figure, and you can see all the impedances which you can present to your device in order to obtain 1.3 dB noise figure. Similarly, better noise figure you want to have, the lesser choice you're going to have. So I can even go further down and try to look at more optimum, kind of noise figure. All right, so the another way to look at it, I know I want, kind of 16 dB gain, and I know I would like to achieve at least 1.1 dB noise figure so that I can have some margin, or maybe 1.2 dB. So you just look at these crossing points. So let's say at this point here, I can see I'm crossing 16 dB gain circle and 1.1 dB noise figure circle. And that's the kind of impedance we are looking at, 8 plus J3, and that's the point. Or there's another crossing point right there, and that is 9.3 plus J7. So around that zone, if you try to match your impedance and the input, you will get a good noise figure as well as the gain. So that's an alternate way of doing it. So two popular ways of how you're managing. Now, if you just want to have a quick feel of what actually I'm looking at, what if I terminate my amplifier in this particular impedance point, what happens to my performance? So let's do that quick exercise. So let's say I want to terminate to obtain the best possible noise figure from my amplifier. If you look at this impedance here, 19 plus J2, I can quickly go to my schematic, and in the source impedance here I can say 19 plus J2, and I just terminate my source impedance with that. We run simulation, and now we look at the response, and now you can see the gamma optimum point is right at the 50. So it's like you did an impedance matching there. If you look at gain is not so great, it's around 14.3. However, if you look at the noise figure and NF minimum, they are kind of at the same place, and that's the whole concept of best noise matching. So you reach the optimum noise point. But here, look at S11. At that reflection coefficient of that impedance, your S11 is not so great. It's only minus 7 dB. Now, for any practical amplifier design, that's not good enough. You at least need better than 15 dB or so. Otherwise, you will have a huge power reflections. So there's no fun designing LNA like that. All right, so let's go back and undo this, and let's change back to 50 ohm, run the simulation again. So that was about the best noise figure match. How about if we try to match it with the best possible impedance? So let's say 8 minus J8. And remember the fundamental, this has to be complex conjugate. So 8 plus J8. And if we do that, impedance matching, we run the simulation and let's see. So if you look at return loss, and now you have an excellent return loss across the frequency band, much better than minus 15 dB as you wanted. S21 is also pretty good. There's more than 15 dB, and we just wanted 14 dB and above, so that's pretty good as well. And look at the noise figure. It has distorted, but not so bad because you are still able to achieve around 1.2 dB noise figure, which is well below your target of 1.4. If you have a tighter constraints like 1.1 dB or so, then this would not have worked because you have crossing the specification. But so far so good. And so that could be one point. Now somebody might be wondering, hey, you just said that having a good S11 and having a decent noise figure is not possible, but I just did a simple S11 based matching, and now my LNA seems to be performing perfectly. So where's the problem? Is a theory problem or there's something else? No, there's no problem. Now let me just undo that. Remember 8 plus J8 for the time being, and let's do a regular 50 ohm simulation. And this is just a coincidence for this particular device, because if you look at this impedance here, where you wanted to achieve that noise figure and you were looking to achieve some gain, so you actually matched your device coincidentally around that point. And that's why your noise figures were decent, your S11 was decent, and your gain was also decent. So that was just a coincidence that that happened. Not, it doesn't mean it will happen in your device. So whether you use this circle approach, that's actually the best approach if you try to use this way, because you know exactly how to balance between gain and the noise figure and pick up the right impedance matching requirements from here. Or you can use this method if you're not sure what's going to happen, right? So choice is up to designer, and different designer works differently. Well, that's how we decided what we are going to do with our matching network requirement. I have now the load impedance, which I have to match. I have the source impedance information, which I have to match. So I can go ahead and use a Smith chart tool in ADS, like I demonstrated in one of the earlier tutorials. And in using that concept, you are free to use either the Smith chart utility, or you could use the impedance matching utility. So choice is yours what you want to do. So here is a circuit where I already did that. So I have a Smith chart component here. You can notice a single stub matching network, and I also use this capacitor as a part of my matching network because I knew I will need to have this series capacitor for my as a coupling capacitor. So while designing a Smith chart, so let me open Smith chart and let's talk about this match. So while doing this impedance matching at the last stage, I included a series capacitor as part of matching network. So I kill two targets with one arrow. I got my matching network as well as I got my coupling capacitors in place. Similarly, for output matching, I prepared a two-step matching. And then also I included a series capacitor here, which is allowing me to reach to the desired load point at the output side. All right, with these two basic things, and I know if you have watched my Smith chart and other impedance matching utility videos, you are pretty comfortable doing that. So the whole idea in this session was to how to find the right impedance matching, what consideration you need to take by selecting the right source impedance for LNA performance that we have already covered. You have already gone through this impedance matching. So once you are done with this, what's our next step? Remember, as we talked about in impedance matching video, these are ideal transmission line components, and they have to be converted into a physical microstrip line configuration. And here you can see it's 25 ohm, 83 degrees length. And we also talked about concept of line calc, and I went through all these steps, how to convert this into a practical microstrip line component, right? So that's what I have done in the next step. And also what I did was to combine everything under a single page of my design here. So I just created two sections, one representing the input match, another representing the output match section. And also we have few optimization goal, because when we are converting from an ideal transmission line to practical transmission line, it might cause some additional loss or mismatch. And at every step, I can just simply run optimization to correct the performance and bring back the required performance from my circuit. So let's push inside, and you can see those circuits here, step 6 and step 6B and 6A for input and output match. So let's look at the schematic behind. So now in this schematic, just focus on the right hand side. So that's the same thing which we had earlier. That's your RC stability network. That's your bias network. And one another good thing to remember, once you fix bias for your frequency of operation, when you are optimizing your circuit performance, for the mismatch caused due to some of these conversions, never try including these components in your optimization. That's not the way I prefer to do it, because once you start managing that, you are also creating this part to be, this section to be part of your matching network. No, this has nothing to do with my impedance matching. If I have done this part accurately, there is no reason for me to change this, section's behavior. Okay, so here is my input impedance matching. So I have single stub and a couple of transmission line and an open circuit stub. The input capacitor, I put the component footprint modeling. And now you can go one step further, which I haven't done in this video. So you can go to Murata or any other vendor, AVX or ATC, whichever company you want to use. You can add those vendor library and change this capacitor to a vendor library component capacitor. So this one is like 0.6 picofarad. You can easily get that value from any manufacturer and replace this ideal model by the library model. However, as we saw in the earlier video, capacitors usually have a very high Q. So I do not expect any serious degradation in my performance of the circuit by changing it to the library component. But again, that step is up to designer. At this point, you change it. In case this introduces certain parasitics, you can still fine tune the performance by changing these width and the length of these impedance matching network to absorb that distortion. All right, so that's how we did the input matching. And then for the output matching is the same, fundamental. I have stability network, I have the bias network, and this is my double stub matching, all converted to practical microstrip line. And here is my output coupling capacitor, again, 6.9 picofarad. So 6.9 not a standard value, so you can easily get 6.8 picofarad. And again, convert it to the practical vendor part if necessary. And so for me, the more important thing was to model the mismatch or the impedance discontinuity, which might be caused by these transmission lines and the footprint of the component. All right, so everything in place, we stack up everything together, we run simulation. When I originally did this, it created a bit of difference, and then I just performed a quick optimization to achieve my desired specification. So here, now I don't need to look at this big data display. I can just focus on these 4 simple graphs. So stability is good, which I would expect anyway. So the noise figure is pretty decent. It's kind of flat from 2.35 gigahertz to 2.45 and well below my specification of 1.4. The gain is pretty decent. I have 2 dB extra margin, so which will be very handy if something goes wrong or during EM simulation and things like that. It's pretty good. The matching performance pretty good, well below minus 15 dB, which was my spec. So all in all, pretty good schematic, microstrip based component schematic performance. Now, as a logical next step, what I need to do, I need to create a layout, and then in that layout, I would like to do a co-simulation to take care of the further parasitics of layouts into my schematic design. Now, again, there are a couple of methods you could adopt. One is to directly create a full amplifier layout and then do a EM circuit co-simulation. The way sometimes I would like to work, and again, as I said, Don't go by my words. Use the technique which works best for you. The way I like to do it, I like to start doing EM co-simulation on a smaller level and then work my way up towards a full complex. So here, as you can see, so I already had input match, but I created a copy of those because I didn't want to disturb any of my previous, worked schematic, so that if anything goes wrong at any step, I can always go back to the previous step and start from there. That's another good tip. And you can see in my flow, this is out of syllabus tip, but having a neat design flow will go a long way in helping you troubleshoot and don't rework everything all the time. So having each step clearly, documented, and you created a flow, and you can see how neat and clean my workspace looks like. So all these things are very, very useful for a designer to manage. However, no textbook teaches you that, right? So it's up to you how you want to organize your work. Right. So in the step 8a, which is basically same copy of my input match, I have the layout, and I created the layout, and you can see I have placed ports at every location where I would like to do my SMT integration later. And here you can see it's like a kind of flat, layout. I have put no spatial effort to squeeze the size, make it smaller. That obviously you would like to do if you are going to fabricate this PCB. And instead of having this, series long line of certain length, you could probably fold it, and you can use tools like this trace here in ADS, define the width of this line, and you can start folding this line the way you would like to. While doing that, just remember to take care of not introducing any additional parasitic coupling. And the good tip to remember while you do that, just keep the separation between these folded lines to be more than 5 times of your dielectric height. That will give you a almost a negligible coupling which you might introduce. Okay, so that's one of the tip, and there are a few other tips which I will cover in the future tutorial videos. So you can use all those techniques to squeeze the size, and you can really make it in a very small size, something like that. But here I just created a flat circuit. All right. Yeah, don't think I have, I'm going to put this onto you to do, design as it is, right? Because then you might end up having a 5-inch, long LNA circuit, which by no stretch of imagination is a good design. All right, so here also in output side, you can see I have a biasing network, stability, and this is my double stub, matching network. And here I have my coupling capacitor, and then finally the output port. And again, you could squeeze the size by changing. And another, good tip to remember when you're dealing with these, and if you find these two stubs very close to each other, because again, it depends what kind of matching you're doing, then you could take one of these, and let me, clear the mesh. So you can take, one of the sections here, and if this step, for example, is coming very close to this step, that might induce a parasitic coupling between them. Your schematic cannot capture that because for schematic, each of these is an individual line. And that's one reason sometimes why people see a lot of difference between when they do schematic design and layout design, they see the performance. So this is one of the reason that sections accidentally starts, coupling with each other, which your schematic will miss, but layout cannot miss because you're running, a full wave EM kind of simulator. So you can take that in case they are coming very close, and you could just use this, shift and Y or mirror. So just press shift X, which is a shortcut for mirroring it around the X axis. Click on a reference point, and you can just rotate that guy. So you can have one stub on that side, one stub on this side, and then there will be no CDS parasitic coupling between them. All right. So some of those tricks you need to remember while creating a proper layout. So I went ahead and set up an EM simulation like we already talked about in previous videos for both input as well as output matching. I set up my frequency plan. Now, another practical tip to remember, take a look at this layout which you're trying to simulate. And using this line, using this port here, you are going to feed a DC to the FET, both at the input as well as the output side, right? So when you run an EM simulation, The EM data should start from 0 gigahertz because that's your DC point. If you just run a frequency or the EM simulation from, let's say, 2 to 3 gigahertz and use that in your amplifier design, and in a schematic you connect a DC power supply here, it won't, this layout won't allow the DC to pass because it doesn't have that result in your EM model, right? So always start your frequency sweep from 0 gigahertz to take care of this DC going to this transistor. Very, very important tip to remember. All right, so once we set it up, we go to EM model, we create a EM model, we create a layout lookalike symbol. And finally, once we finish both of these EM simulations, we go to step number 9, which is co-simulation. And here you have the co-simulation schematic. And you can see this is the input matching layout. This is the output matching EM component. And this is the DC bias supply. Remember, I just talked about it. So this has to go through to reach to FET. And similarly, this drain supply has to go through and reach this FET. And again, if you a lot of designers reach out to me and say, oh, everything was working very nicely when I had a schematic, but when I did EM co-simulation, my amplifier started showing loss. It is showing me minus 40 dB, minus 60 dB instead of plus 10 dB gain. And this is one of the very common cause. And to quickly troubleshoot while you are here, you can just quickly switch on the voltage annotation and you can see the voltage is pretty there. If your EM model had a problem and this component didn't allow this current to travel there, you will see that as 0 volt because there's no DC supply reaching to that point. Similarly, you can also switch on the DC current annotation, and here you can see you have the DC current going into this device. So everything is good. All right. So how to operate all of these, please refer to the DC simulation and a video on my YouTube channel. All right. Once we have everything, just go ahead and hit simulate. Look at the performance. It's pretty much the same. Slight degradation in noise figure due to additional loss. And you can see that additional loss also impacting the gain, which was around 16 dB or so before. Now it's 15.6. But the real loss is pretty good. Gain is above the required specification. Noise figure is below the specification. So everything's pretty good. So when I validate the input and output section separately, now as a final step, I can go and do a final layout. So this is how we do final layout. And I already talked about some of these, like the plane creation in one of the earlier videos, how to insert the array of the VRs. But here I did one more change. When I'm simulating this PCB, I included con2 as my ground layer. And I modified my stack up to represent con2 as my ground layer instead of using cover plate as an ideal ground. And I do have the whole mapping to connect between con and con2. All right. So by having the right material with the right configuration here allows me to do a proper EM simulation. Now remember the ports. So at every location, if I just switch off these guys here, so if I switch off those and switch off the lead and the text, and now you can see you have a one port here, one port here, one here, and one here. So these are 4 for FET, and then correspondingly for inductor capacitor. Now, when we do that as a practical design tip, focus on the area where you are going to mount the FET on these kind of PCBs and make sure you have sufficient via holes around that active device. Because if you don't have enough vias, and let's say sometime you only have one via on this side, one via on that side, remember the source terminal should be connected to ground, and it should be done without any serious inductance. Otherwise, that will form a kind of series feedback when you have the inductor connecting to ground, and you will create a feedback loop. So that's why I prefer to have more via holes around the FET device to make sure even if there is some parasitic inductance, it gets divided by factor of n due to multiple via holes. Okay, this will give you a lot of advantage when you do these kind of designs. And you will see that just now when I show you this fully integrated EM simulation performance. All right, so once we have this, we just follow the same process of creating EM model and symbol, and we do a final NLA layout co-simulation. And here under one piece, you have the EM model. But again, remember the EM model simulation range should be 0 to the frequency you are working at. All right, so once we have this full board EM and we run the simulation, now you can notice here the noise figure reduced a little bit, which is a good sign. The S11 is pretty much well under specification, which we wanted. S21 is also pretty good, better than 14 dB. So I still have 1 dB margin in case something goes wrong in fabrication. And here, remember, I haven't accounted for input connector, output connector, and those connectors will also have some incremental loss. So I'm well below the specification limits and meeting all the specifications here. So at this point, I can say that my performance of LNA for the linear range. So if you look at the specification which we originally had around the frequency range, I wanted gain of 14 dB, return loss of better than minus 15 dB, noise figure of less than or equal to 1.4 dB. So all of these linear performance specs are met at this stage, right? And we have taken all practical considerations into account. So at this point, our 80% of job is already done. We have a pretty good working LNA circuit. Now, if you were working with this parameter model and you didn't had this nonlinear model, there is no change for any of the steps which I mentioned here, except you can't do step number 1. But apart from step number 1, the only difference is like I'm using this FET, you would be using an SNP, that's it. But rest of the process is exactly the same. So at this point, if you don't have a nonlinear model, you can go ahead and generate a Gerber file for this layout and proceed for fabrication. And everything will be working out good because there is nothing which I have left for assumption or nothing which I have left on fate to let that thing happen and I have a surprise. There's no scope of surprise here. Okay, right. But if you are dealing with a nonlinear model, you have one extra step, and that is to comply to P1dB and IP3 specification. And that's what we are going to cover in part 3 of this tutorial, because there is a slight difference how you would approach an EM simulation setup if you know you are going to do a nonlinear simulation later. And after we do nonlinear validation of our EM circuit co-simulation, we will go and also look at EM circuit excitation, see the fields, how they are distributed by structure and so on. And finally, once I'm happy with everything, we'll go ahead with Gerber generation and do a performance benchmark without off-the-shelf LNA. All right. So take a well-deserved break. It's been over half an hour in the last part, and I look forward to see you in part 3 of this tutorial. Hi, welcome back to this tutorial on LNA design. This is part 3. You are doing an excellent job staying with me till now, and hope you will have a further learning to enhance your design experience by looking at some of the tips I'm going to give you to set up EM simulation, in a most efficient manner as far as possible. If you want to use that EM results to run a nonlinear simulation, and then we do our nonlinear validation of our LNA design and verify for the nonlinear performance as we need, as part of our, design spec. And then we will take a look at how can we get further insight using EM circuit excitation feature to make sure we have a complete understanding of our circuit operation at various frequencies, at different power levels, and so on. Once we are fully satisfied, we'll go ahead and do a Gerber file generation for our amplifier, which will be the final design step in this tutorial. And then as a completion sake, just to give you a confidence on how well we did, we are going to benchmark our performance with an off-the-shelf LNA component, a product sold by a very famous company. All right, so let's go through this last part of the tutorial. All right, so just to quickly summarize what we did in the part 2 video, just in case you took a longer break. We finished our LNA design and a complete linear characterization using the EM co-simulation feature. And we run this analysis and we fine tune all the performance and make sure we have all the specification met for all the linear operation. Now, as a final verification process, we need to do a nonlinear simulation. Now, in order to do that, the layout and the layout doesn't change anything, but how we set up EM simulation differs slightly. So let's talk about it. Now, if I open EM setup here, the main difference here is how you set frequency plan on the EM simulation side, so that this component or this layout model is useful for running a nonlinear simulation, whether you are doing a transient simulation, harmonic balance simulation, or even circuit envelope kind of analysis. All right, so in a traditional way, how we set up the frequency plan, we have a single adaptive sweep and we go from DC to the required frequency point, which we are interested in. However, remember when you want to do a nonlinear simulation on any circuit and you have an active device in place, you are feeding a fundamental frequency. So obviously that has to be covered, right? And the device has to be DC biased. So that means your component should at least have the DC point as well as the RF frequency, which you are interested in simulating. Now, when you do nonlinear simulation, you need to think a little more. Because if you were just using an S2P file for your LNA design or any active circuit design, that's enough, right? You don't need to even worry about the DC because you don't feed the DC. It's just an S2P file. So it is fully sufficient if you just run simulation within your frequency band, let's say 2 to 3 gigahertz for this case. But here I'm using a nonlinear transistor, and I'm also interested in looking at the harmonic performance and IP3 or IP5 kind of specification. I need to set up simulation slightly differently, and here it is. So in approach number 1, which is like a blind approach, you can start from 0. Make sure the f-stop covers your 5th or 7th or whatever harmonic you may be interested on, and you can set up a single sweep covering the entire frequency range with the required number of points, and you can run the simulation. Now, this approach is okay if you are doing maybe up to 5 gigahertz kind of amplifier, because you can do a single sweep from DC to 25 gigahertz and everything is fine, right? Although that's not most efficient way, but it's still manageable on most of your application cases. But think about if you're doing 10 gigahertz design or a 15 gigahertz design or a 20 gigahertz design. And if you want to do it this way, then you might need to start from 0 and go all the way up to 70 or 80 or even 100 gigahertz with a single frequency sweep. Will that be economical? Will that be time friendly? The answer is simple no, because you end up wasting a lot of your time and memory in the frequency spaces where you have virtually no energy or not any interest in those frequency zone. So the way we resolve this problem is by setting up a segmented frequency sweep. And this is exactly the technique which anybody would even do on instruments like a vector network analyzer or VNA. When you have ultra broadband measurements to be done on VNA, if the entire frequency range is of your interest, then you have no other option but to set up a single sweep with a desired number of points. But in case you are working on a situation where you have interest only in a specific bands, then you don't waste your calibration points, a number of measurement points scattered through the entire bandwidth. Rather, there we create these kind of segments and we only set up the simulation in the band which we are interested in. So in my case, this is approach number 1. The approach number 2 could be I set up one frequency sweep from 0 to let's say 100 megahertz, and that will ensure I have the right circuit performance for the low frequency so that I can take care of the DC and the low frequency content very well. The second segment could be centered around my desired fundamental frequency point. So let's say between 2.2 gigahertz to 2.6 gigahertz, so that I have certain bandwidth around my carrier frequency. Then the third could be centered around the second harmonic, third harmonic, fourth harmonic, and the fifth harmonic. So this way, when we set up this simulation, I'm not wasting my time in simulating anything between 5 gigahertz and let's say 6.6 gigahertz, from 7.5 gigahertz to say 8.8 gigahertz, because virtually we are not even interested in looking anything of that sort in our amplifier design, right? So that's the proper utilization of the time and memory. Plus, your simulations will run much faster because you're not trying to sweep it in an ultra broadband, kind of space. All right. So always remember to set up the right frequency segments, which are the ones which you're really interested about. Okay, around a DC point, around fundamental points, and the desired harmonic points. All right. So in my case, what I have done, because I can manage it, so I just ran a single sweep from DC to 12.5, and I enabled that. You can see rest of the points are not enabled. That means ADS will ignore that while running an EM simulation. And then, because later I know I wanted to use EM circuit, excitation feature, and I would like to see the current profile inside my structure. Along with while doing a wide frequency sweep, I also added a linear frequency sweep at my fundamental frequency till the fifth harmonic with a number of points of 5, so that I will do simulation at 2.4 gigahertz step. So essentially, I will cover my center frequency and the second harmonic, third, fourth, and fifth harmonics right there. So I should be able to visualize the current at all my desired frequencies. All right. So that's the only difference, and that's how you set it up for a typical nonlinear simulation. All right. So after this, you can go ahead and simulate, and the rest of the process is same, and you end up getting the same kind of component. But here you can see I'm referring to step 11A component, which is nothing but this setup here, and I have an EM model generated for HP. All right. So, and this is just a name. I mean, by default name would be EM model, but I just suffixed _ HP to differentiate it. All right, so with this, we set up a harmonic balance. And again, I already have a tutorial video talking about how do you run harmonic balance simulation, one tone simulation, two tone simulation, and all that. So here, already set up an harmonic balance simulation. I have a node here called V out. We run the simulation, look at the fundamental output power. So notice what we are feeding at the input is Pin of minus 30 dBm. And what I have as output is minus 15 dBm. So it's representing 15 dB gain as my S parameter simulation was also showing. And this is just a time domain waveform at the output indicating there's no compression, nothing. It's all linear operation. And you can notice the second harmonic is very, very small. This is for the two facts. One, remember we are operating on class A. So anyway, all the intermods, all the harmonics will be down. This is even further down. If you compare, it's like minus 15 and this is like minus 100. So it's almost like 87 dBc down. And the part of the reason is in our bias network. Remember when we talked about this bias network, this lambda by 4 becomes lambda by 2. For the second harmonic. So even if I have the impedance matching network, which will reject second harmonic, but this guy will suck up the second harmonic, and through the relevant capacitor, it will go to ground. Although right now I don't have a suitable high frequency, decoupling capacitors. In your actual board, it's not only one capacitor, you may be having 3 or 4 catering to different kind of frequency bands here. All right, but this is how this energy and the second harmonic will go down. So this bias impedance line itself is acting as a natural notch filter for my second harmonic. All right, so once we set up a normal harmonic balance simulation, I can go to power sweep, and I have another test bench again. I have done this for more clarity purpose. You could only do it in one schematic itself here. But because I need to produce this video tutorial, so I'm doing everything in a very detailed manner. All right, so here with power sweep, I'm sweeping P in the harmonic balance from minus 30 dBm to plus 10 dBm at the input and a step size of 1. And we will run the simulation. We look at our swept power performance, and here we can see input versus output power curve, and also the gain compression. And at 1 dB compression, because my nominal gain is 15 dB, at 14 dB gain, the input power is 0 dBm, and at input 0 dBm, the 1 dB compression point is plus 14 dBm at the output. So pretty good. So, and our target was greater than plus 10 dBm. So we are meeting that target. All right, this is how just an additional information, second harmonic, third and fourth and fifth harmonic is changing with respect to power. All right, so one more checkpoint in our specification that we have a P1 dB of greater than 10 dBm. So we met the spec. Now final spec to validate is IP3. So let's go and look at it. And again, we already have a tutorial video on how to set up two-tone two-tone nonlinear simulation. So exactly the way I talked about in that video. So I have plus minus 1 megahertz offset between the two tones, and I'm feeding P in, and that P in is defined as minus 30 dBm, and you can play that value. And then from the list of measurements from simulation harmonic balance palette, I do have this IP3 out, and I'm placing this IP3 out, and I'm just using a third order calculation for this point here. So let's go ahead and run simulation. Again, no major surprise. My output IP3 is 28.5 dBm, and this is how my two-tone intermodulation products looks like. And again, everything as expected is very low because my LNA is operated in a purely linear region right now. Okay, so again, if I go back and check at my spec, it was supposed to be more than 20 dBm, and now what I have is plus 28 dBc. So pretty good. All right, so this kind of completes my complete LNA design flow. But here comes the bonus. If you want to understand how all of these things are working internally, so I'm going to open the power sweep because that's pretty interesting. So if you look at this power sweep is schematic, where I'm sweeping the input power level from minus 30 dBm to plus 10 dBm. In the last tutorial video posted on my YouTube channel, we have this EM circuit excitation. So let's invoke that. In EM circuit excitation, as we talked about earlier, we have all these simulators which are supported. So here we have an harmonic balance. And if you have an S parameter simulation along with harmonic balance, this utility cannot run because in S parameter simulation, we don't force any excitation or we don't feed any excitation power or voltage to our structure. Okay, so only simulator which you find missing here is an S parameter, which is understandable. All right, so let's click run simulation. Simulation is done and compute excitation is all finished. However, in this case, I'm not going to draw far field because I'm not designing any antenna or anything. It is just an LNA circuit. So the only thing I would like to see is the current visualization. I don't want to see the far field here, so I don't want to check that. And the analysis is HB1, which is this analysis here. All right. So once we start visualization, and as usual, ADS will inform us that you have not simulating the circuit for 12.5 gigahertz, which is fine. Click OK. And what we are expecting is only 5 frequencies, 2.4, 4.8, and then third harmonic, fourth, and then finally 12 gigahertz, which is fifth harmonic. So here is my 3D preview window or 3D far field or current visualization window. And again, you can see all the ports which we originally have in the layout, so no surprise. And these are your frequency contents, which you can plot up to 12 gigahertz. There'll be no current at 12.5, all right? But anyway, so as we discussed, we are not going to feed manual, because if you're feeding manual, you can see I can excite the structure from port 1, but that structure doesn't go forward because now there is a gap here and there is an SMT component. So traditional EM simulator cannot fill this gap. And for that reason, we will use extracted excitation, which is basically reading the the circuit excitation here. So now I have connections made between all these ports. And now you can see currently at DC, this is how your DC current is on your structure. And obviously you can see the red color here because that's your drain current, and gate current is very small with respect to the drain current. But if you accidentally created some short circuit, let's say I didn't put this capacitor here, then you will see this also light up because then the current is going through uh, that path to ground, and suddenly you will find, oh, I have a problem about my DC biasing in my design. So it gives you valuable insight about your current distribution. All right, so let's switch on our 2.4 gigahertz, and now let's go and animate. And now I'm feeding certain power here. You can see slight color change here, but you can see color is more. Now I'll give you a few seconds to think why you see less density here and why do you see more density there. What's the difference here? Think about it. All right, no prize for guessing because you have an amplifier device here, right? So whatever excitation, let's say minus 30 dBm, and if you go and look, currently we are looking at minus 30 dBm. So the power available here is minus 30 dBm, and here you have a 15 dB gain. So here you have minus 15 dBm. So obviously you have more current propagation going through. And as you increase the power level, so let me use my arrow key and I switch one by one. See what happens here. Now you start to see more denser current because now your output power is increasing. So your current density is increasing, and now you start to see everything starts to light up once we reach closer to minus 15 dBm input. And now you can really see how the currents are, distributed across your structure. Now, this is also very useful in case, at a certain power level or at a certain frequency level, if you have unwanted resonance, you can quickly capture. Let's say my desired direction of the current propagation is it should reach the output port. But if I have some accidental short circuit here, due to lambda by 4 open or whatever, unintentional, I will see the entire current getting sucked up here and virtually there is nothing going out. And that gives you a very good circuit level insight. So this is like a live, I would say current spectrogram, as if you're fully, your circuit is fully loaded on the PCB and you are testing the live performance, looking at the current visualization. Okay, so once we reach the input, compression power point, let's say 0 dBm, we can see how the currents are scattered in our structure, and we can see all the current density information. And again, you can change this density level by changing the level here just to keep everything in control. All right, so that was about fundamental. Now, if I want to see how the harmonics are distributed in the structure, we can click on 4.8 gigahertz. And as expected, you see what's happening here? That 4.8, which is second harmonic, is getting sucked up with this bias, network, because that is acting as a perfect, lambda by 2 line. Again, reinstating my statement here, just validating the statement which I made. And that's how the current is propagating through. And you can see there's virtually no current coming out at the output because the second harmonic level is very, very small. Similarly, you can go and inspect all the performance. You can see the third harmonic. It has a partial contribution, but you have third harmonic is still traveling up to this point. And finally, this matching network is kind of suppressing that third harmonic. Now let's look at the fourth harmonic, and again, as expected, this again will become like a lambda long line for the fourth harmonic, and again you start to see the activity going to ground. All right, so that's what I meant by having further design level insight at using the EM circuit excitation. All right, so let's go back to our agenda, and we have covered all the points from top to bottom in a very, very logical manner. I hope you guys enjoyed watching all the tips and tricks going over the complete design flow. Finally, we have to generate a Gerber file, so let's open ADS. And now we can open our final layout, which we did in step number 10. And from here layout, remember we have 3 layers: contour, cond and the whole layer, which eventually we would like to generate a Gerber, and this text is written in a certain layer. Now to generate a Gerber file, go to File, Export, select the Gerber file format. And again, I have a separate tutorial on how to generate Gerber files. So I'm not going to go into greater detail, but I would like to view the file after export. I can go into more options. I can select what options I want, select all the layers which I would like to export in a Gerber file, select the drill information, and here I only want to export the drill on whole layer, which are my actual layers. Click OK and click OK, and now you have the whole Gerber file. And again, you can switch off everything, only look at con. That's your main design, and then the name which I pointed there, and then finally the whole layer, and that's what your Gerber file is. All right, so where are these Gerber files and all that? We can quickly right click, explore it in file system, and in the file system you have manufacturing folder, and in the manufacturing folder you have this step 10, which we just use step 10a, and there you have the Gerber file and rest of the file which you have. All right, now as a final step, let's open our internet browser and look and search for a part. So here I'm going to just type an LNA, and here when LNA comes up, and we can see there's a company here called Skyworks, and that's a very famous company producing LNA. So let's go to their website, and from their website let's go to low noise amplifier, and from the list available here you can notice what kind of parts they have. And if you look around the frequency range we were designing, so we have a part here around that frequency. So if you open that data sheet, you can see the gain is 13 dB, noise figure is around 1.1 dB, low current consumption around the same, DC power supply and all that. So this is aligned very nicely with the LNA we just designed. However, the big difference is, look at the size of this circuit. It's only 1 mm by 0.7 mm by 0.5. And the reason for that is it is an MMIC amplifier. And what we did is a board level design. So we really can't compare the size here. But in terms of performance, we pretty much did as job as these companies do, and the great designers working in these companies too. All right, so that's the end of this pretty long tutorial, but I hope every section which I covered gave you some design level insight, which you wouldn't have found even if you would have read 2 textbooks on amplifier design. And now you know how to really take all those theory, put it together, and generate a final product for yourself. All right, so in the end, thanks very much staying with me till the end, and hope you enjoyed the deep diving session we had in this tutorial. And don't forget to subscribe my channel, share the link with all your friends and colleagues in various forums you may be member of. And of course, don't forget to hit the like button. Have a great day and good designing experience with all these tips and tricks. Thanks a lot for your attention.